Hi, this is Shirley Physics, episode on Rotational Kinematics. Rotational Kinematics is just like translational kinematics. The equations are the same, they work the same way, all the concepts are the same, they just have a slightly different look. Introduced in the last video how instead of displacement, we now have angular displacement. Instead of velocity, we now have angular velocity. And instead of acceleration, we have angular acceleration. So just replacing those x, v's, and a's and all the straight line motion equations, instead of x equals x initial, I guess we could probably say an x of t. Our x of t function before was an initial position plus initial velocity times time plus half at squared. Guess what? Now we've got a angular position with respect to time equals initial angle plus omega naught t plus half alpha t squared. So equations work out the same way. Instead of our second one, vf, or a v of t equals initial velocity plus acceleration times time, we now have omega t. Omega is a function of time. Initial angular velocity plus angular acceleration times time. And we also had a relationship between a final velocity and an initial velocity if there's a change. There's a delta x at the end there. We'll also have omega final squared equals omega initial squared plus 2 times alpha times change in theta. Now again, what's very important to note here is that these are all for constant angular acceleration. Let's say you turn on a fan on high, you can assume there's a constant angular acceleration, at least until the fan blades get going. There might be some drag later on, so that angular acceleration might decrease. But you can also look at it as the average angular acceleration instead of an instantaneous. If we were to look at the instantaneous forms, of course, you might recall that v equals dx dt for an instantaneous velocity. Then we've also got an omega equals d theta dt. See, everything translates exactly the same. We're just looking at it in a new view. And of course, for acceleration is dv dt. For instantaneous acceleration, alpha is d omega dt. Everything works the same. That being said, just for a visual, keep in mind that these equations over here for like side-to-side motion, up or down, in or out, north, south, east, west, those kind of motions. Or over here with rotational motion, we're generally dealing with a rotating body, maybe a disc or a bar. Those are general shapes, and they might rotate counterclockwise or clockwise, and generally they're spinning about some rotational axis. So there's a direction there. Instead of left, right, up, or down, we have clockwise and counterclockwise, and those go for rotation instead of translation. And finally, you might recall that given a velocity time graph, something like this, the slope of that velocity time graph is the acceleration rate, and also if we find the area underneath the curve, that would be the displacement of the graph, or displacement of the object. Likewise, if we have an omega versus time graph, so the angular velocity of an object, how fast its spin is, let's say it starts with a negative spin and decreases its speed to 0 and then becomes a positive spin. You can call positive clockwise or counterclockwise. Later on, we are going to define positive as mainly a counterclockwise motion. It goes along with the right-hand rule. That's much later. But anyhow, there is a direction to spin. So if you do find the slope of the angular velocity versus time graph, the slope of an angular velocity versus time graph is going to be the angular acceleration of the object. So that's the rate of acceleration. And also, if you again, determine the area in there. Guess what? That will be the angular displacement, how much angle the object is rotated through. So everything translates from translational motion to rotational motion. Now, one last piece I want to add here. All right, let's say we've got an object that is moving, it's rotating about a fixed point. Or we could look at a point on the surface. Let's call this like a turntable, a vinyl player, record player as we used to call it. Or it could be a merry-go-round. This could be a person at the edge of a merry-go-round. Okay, that might be the best scope to use here. That person at the edge of the merry-go-round would have a tangential velocity as the merry-go-round rotates counterclockwise. All right, but what else would be happening here? That there would be the person would have to hold on to those bars, so there would have to be a centripetal force holding that person in, and as you call, centripetal force always acts toward the center and causes a centripetal acceleration. So a centripetal acceleration is something we learned about in the past. A centripetal acceleration can also be called a radial acceleration. It's an acceleration rate that changes direction, that is directed in towards the center and along the radius of the circle. So this is called a radial acceleration. A centripetal acceleration can also be written a radial or radial acceleration there. All right, and of course you might recall that that has a relationship v squared over r. Now what happens if there is an angular acceleration? You see this radial acceleration is going to be there whether or not the object is speeding up its spin or slowing it down. Remember, this is a acceleration that changes a translational direction. This is what's causing the person on the merry-go-round to stay in a circular path. Remember, if they let go, then they're going to be separated from the merry-go-round, no longer spin. So as long as there's a velocity, there's a radial or a centripetal acceleration. If that velocity increases, if this tangential velocity increases, then the radial acceleration is going to increase also. They're going to have to hold on tighter. The centripetal force has to be increased so that they stay in that circular path. But if there is an angular acceleration, you might recall that there's also going to be a tangential acceleration, an increase to their translating motion as this person goes around. And that's in reference to the angular acceleration. So in a previous episode, I introduced S equals R theta, and take the time derivative of that, you get V equals R omega, and again the time derivative, you get A equals R alpha. And that's the relationship between the edge acceleration and alpha. And this is stemming from the arc length and its angular displacement there. All right, so if the spin increases, if you're on the edge of this merry-go-round and you push on the ground more, and you're spinning faster and faster and faster, you increase the rate of turn. The angular velocity increases. So there is a tangential acceleration also if there is a non-zero angular acceleration. So if we focus mainly on the tangential acceleration and centripetal acceleration, you'll note that these two vectors form a sum. The overall acceleration of the object at this point, now that's not a very straight sum there. Okay, that's a little bit better. And so if this is the length of the resulting tangential acceleration from the angular acceleration of the merry-go-round as it gets faster and faster and faster, then there's going to be a component of tangential acceleration that is tangent to that circle. There's also going to be a radial acceleration going inward. I have a lot of extra things on the screen here, so I'm going to just focus mainly on that tangential acceleration, and let's start calling this a radial acceleration here. So we have the radial component and the tangential component. Okay, the red and the white causing the green. So if we were to put those two together, that green resultant acceleration would be the sum of the white and the red. There's the white and the red. There's our radial component and our tangential component. All right. The tangential component being r alpha, so that relates to the angular acceleration, and the radial component being v squared over r. Notice they're both radius dependent, and we put them together for the resultant acceleration. And of course, a squared equals at squared plus ar squared. So this is nothing to memorize, just a concept to be aware of, that a spinning object or spinning system that is increasing its spin is going to have an acceleration that's not just toward the center and not just tangential, but a little combination of both. When we do put those together, we'd have an r alpha quantity squared and a v squared over r quantity squared. All right, so just keep that in mind as you go through. Occasionally, this quantity is asked for. What is the resulting acceleration? It depends on both the tangential component and that radial component. So just trying to package all this stuff together. So this should be a good introduction to motion. What you need to do now is definitely practice using those kinematics equations for rotation. And once you practice it, you pick it up rather quickly because you've already had experience doing that from our Unit 1. I hope this becomes helpful.